So welcome to this, the Further Maths Support Programme online revision session for MEI Statistics 2, and in this session we're going to be looking at using the chi-squared test. So it's not a huge topic this, but again it's one where lots of questions come up. So we are required to apply the chi-squared test in a contingency table setup. We are then asked to be able to interpret the results of a chi-squared test and effectively perform therefore a hypothesis test. But we're also expected to comment on the contributions that each category makes to the chi-squared test statistic and what that implies in terms of each category. And this does restrict the techniques that you are allowed. There are some fast techniques for using chi-squared that don't allow you to see contributions. And I'll talk about what contributions are a bit later. But it's quite important that you know that. So, June 2010 question 4. We've got a survey of 63 runners, and the category of runner and type of running are classified as follows. So there are 3 types of running. There are 3 categories of runner. So in total, you can see that we've got 9 categories altogether. Okay, just put dots next to those so you can see them. And we've also got column totals and row totals and a grand total. And we are required to carry out a 5% significance level test to examine whether there is an association between category of runner and type of running, stating carefully null and alternative hypotheses. Okay, and we should have tables showing contributions. So they're specifically asking you here for tables of contributions, because again, the question is going to demand us talk about them a bit later on. Now, the thing you need to understand about a chi-squared test is we've seen the idea of an association before when we're doing Spearman's rank, and generally when we're asking for an association it's because we're dealing with non-parametric data. Now here this is actually qualitative data because these are just categories. So when you state your hypotheses, we have to use words. So your null hypothesis, so nullity, is no association. Now if you just write no association, you're going to get no marks, okay? We need context, so no association between category of runner and type of running. Okay, and H1 would be an association. Okay, the mark scheme says some association, but really, when we do these, we are looking for an association or not. It's hypothesis testing at this level is very black and white. It is or it isn't. So an association would be fine. So an association between category of runner and type of running. Okay, so to do this, what we need to do is we need to work out what's called expected data. So here we have the idea of observed data. That's what we see. And here we're going to work out expected data. Okay, now each cell, I'm going to label this one, has a name. This cell is E11 and this cell here is O11. Okay, now they correspond to row 1, column 1. So to work out E11, what we do is we take the total from row 1, which is this one here, multiply it by the column total, which is C1, and we're going to divide it by the grand total. Okay, and we do that for every single entry. Okay, so this entry here, if we do this one, I'm going to show you something interesting in a minute that can be used as a check as well with these. So we're going to do 19 times by 17 over 63, and if we work that out, that's going to give me 2.9257. No, it's not, 5.13. So that's my expected value. Okay, we can do the same for senior, same calculation, and that's going to give me 7.84. I'll convince you of that. So that's E12 is going to be row 1 times column 2 over grand total. So it's going to be row 1 times by column 2 over the grand total, and that's going to be that one. I'm then going to work out these two, and if I do that in the same way, that's going to give me 6.48. and this is going to give me 9.90. Now, bit of advice here. The degrees of freedom, which we'll talk about in a minute about this, is the minimum number of cells required to be filled in to generate the rest of the table. Now here what I can do is I can actually generate every other value. Because I know these two values in the row, I can actually work out track veteran. I can also work out road veteran, because the column and row totals must be fixed. Likewise, I can work out both running in each cases and then the final one. So here I have 4 degrees of freedom. There is a quicker way of doing this, which is row minus 1, column minus 1, which is going to be 2 times 2. So it tells me that there are 4, but it allows you to speed things up. So what you can do is then, to work out veterans, you can do 19 minus 5.13 minus 7.84, because these have to add up to 19. So this gives you a quick way of working all these out now. Okay, 7.62, 5.40, 8.25, and then as a check mechanism you can work this one out as 6.35, but what you can also do is you can check by working out E33 using the formula, row 3 times column 3 over grand total. If they agree, you know that this table is correct. Okay, now it's a really important thing to make sure these tables are correct, because it's going to cascade through and you're going to get compounding errors. So by understanding this concept of degrees of freedom here, it gives you a quicker way of filling in the table, which is good, but also then gives you a check mechanism as well, which I think is a very, very sensible thing. So you're going to get 3 marks for doing this table. Okay, so it's 1 mark for your hypothesis test, 3 marks for this. So you get a method mark for demonstrating some form of approach at finding all these e-values. You then get A2 for the table correct. You get A1 for at least 1 row or 1 column correct, and A2 for the rest. So it's a lot of work just for 2 marks. Okay, so there we go. That's all of those filled in. So the next thing is we need to work out these things called contributions. So a contribution for each one, contribution, I'll work out a couple of them and then we'll go from there. You need to work out all 9 of these separately. So a contribution is defined as being O minus E squared over E. Okay, so if we look at the contribution in cell 1-1, okay, so contribution in cell 1-1, that's going to be observed value minus expected value squared over the expected value. Okay, and that's going to give me a value of 2.9257. And you're going to have to work all of these out. So x12, which will link seniors, is going to be 8 minus 7.84 all squared over 7.84, which is going to give me 0.0032. Okay, so you would do this for all of them. So let me just describe how your marks are kicking in. You only get 2 marks for this, so you've got to make sure it's right. You get a method mark for demonstrating that you're working out O minus E squared over E, and then you get an accuracy mark for getting all of your contributions correct. Okay, so we're getting there. We're now up to what? 1, 2, 3, 4, 5, 6 marks. 6 of these 12 marks. Okay, so now we need to be able to calculate the test statistic. So I'll do this on this one actually. So the test statistic is effectively x squared, and it's going to be the sum of all of your contributions. Okay, so you're going to add all 9 of these contributions together, and in this particular case it's going to give you 10.21. Okay, so the sum of all of my contributions is 10.21. Okay, so sum of all contributions is equal to 10.21, and we've already decided that we have 4 degrees of freedom. Okay, just to remind you, the degrees of freedom is number of rows minus 1, number of columns minus 1, which is 3 minus 1, 3 minus 1, which is 4. So we've got 4 degrees of freedom on the chi-squared table, and we're looking that up at the 5% level. Okay, so at the 5% level, with 4 degrees of freedom, we've got our chi-squared value as being 9.488. So your chi-squared, sorry, your x squared is 10.21. That is your test statistic, by the way. And we've also got chi-squared with 4 degrees of freedom at 5% is equal to 9.488. And that is your critical value. Okay? And we can see here that your test statistic is greater than your critical value. Okay, so like we did with the hypothesis testing and all the other bits and bobs we've done, this statement leads us to reject H0. So we're going to reject H0 in this particular case. Okay, so there is sufficient evidence to suggest an association between, and again you've got to contextualize this, so between category of runner, and again don't shorthand this, write it exactly as it is, and type of running. Okay, so this statement's really quite important here. Okay, so you're going to get 2 marks for working out your sum of contributions. You get B1 for working out the fact that you've got 4 degrees of freedom, and you get another B1 for reading it from the table correctly. So you get a lot of marks here. Okay, you then get another B mark for rejecting H0 and an explaining mark for getting it out. So you can see all of that computation now comes down to this. Now you can see that because these are B marks, then it doesn't matter too much if you've made mistakes previous. You are going to lose marks obviously if your accuracies are not correct earlier, but because these are B marks, it doesn't have that much of a major impact going on through this question. Okay, so we are now asked to talk about the contributions of what's going on. Okay, so for each category of runner, comment briefly on how the type of running compares with what would be expected if there is no association. So these are contributions to the test statistic, and they are all O minus E squared over E. Now you can appreciate that if that's 0, there is no contribution. Okay, so therefore there is effectively things are appearing as we would expect them to, because O minus E observed would equal expectation. So if this is 0, then this is implying that O is equal to E. Your observed data is equal to your expected data. If it's quite big, what it's telling you is that that is the biggest contribution. Okay, so it's telling you that more often than expected. So if we look at the first column first of all, this is the number that stands out here for juniors. So let's look at junior first of all. So they appear, because this is a big contribution, juniors appear to be track runners more often than expected, and these are quite small in comparison. So these we would say that are less often than expected. Okay, they're still, different from O minus E, but you just need an awareness of that. Okay, so that's what we say here. So juniors, bigger contribution. So juniors appear to be runners more often. Okay, it also ties in with your observed data as well. If you go back to your observed data for a second, okay, it's also bigger than you would expect. So if you looked here, it's 5.13, wasn't it? Okay, these were 6.48, 5.40. So when we talk about more than, it's a combination of these as well. Okay, so 9 is greater than 5.13, and you have that bigger contribution. Whereas if we look at seniors, there is no major outstanding sort of contribution here. So everything here is pretty much acting as expected. Okay, so we're basing it on the contribution. So seniors are as expected. Okay, now here if we look at veterans, these two contributions are big, this one is quite small. Okay, so again, going back to your data, if we look at veterans, okay, we've got 6.03, we've got 7.62, and we've got 6.35. Okay, so here we can see that they tend, this is bigger, so they tend to be track runners less than expected. We can see that because because this is quite big, it gives us something to think about. So again, you go back to your data and you can see that your observed data is less than, so we can state that. So here, veterans are more likely to be roadrunners, sorry, and less likely to be roadrunners. Okay, this is pretty much as expected, so I'm not so really worried about that. So you need to use your contributions to indicate that something is more than it should be, or they differ more than they should be. So we're looking for your O minus E squared over E to be noticeably bigger than 0. That then causes you to look back at your original table to make sure that you're getting your correct way round when you're discussing these. Okay, so students do find this quite tricky, and it's worth a lot of marks. So basically, you get 2 marks for each. Okay, they're explaining marks, and you do need to make sure that you are sort of making context here. So don't just say juniors appear to be as expected. We need to sort of justify it. So again, it is going back and looking at these values that you need to be able to do here. Okay, so again, all the chi-squared questions are pretty samey, but that does cover a typical hypothesis test.